You've conducted a literature review, and now you have a research question. Let's take a look at the data.
Raw data consists of long lists of numbers and labels that don't seem to be very informative. Raw data lacks context. Exploratory data analysis is what you use to make sense of the data. You do this by converting data from its raw form to a form that makes sense, that has context, that tells the story you want to tell. Basically, exploratory data analysis consists of organizing and summarizing raw data, looking for important features and patterns in the data, looking for any striking deviations from those patterns, and interpreting your findings in the context of the problem or research question. We begin exploratory data analysis by looking at one variable at a time, also called univariate analysis. In order to convert raw data into useful information, we need to summarize and then examine the distribution of any variables of interest. By distribution of a variable, we mean what values the variable takes and how often the variable takes those values.
If we were studying a small number of observations, we could do this with a pencil and paper, a calculator, or even in our heads. The data sets you're working with often have thousands of observations. Working with such large samples is only achievable if we use statistical software. These software programs require the use of syntax or formal code to retrieve, analyze, and manipulate data. Learning to write code, learning the proper use of syntax, can really expand your capacity for engaging in statistical applications and is a central skill you'll learn in this course. This skill will also greatly expand your capacity for engaging in deeper levels of quantitative reasoning about data.
For this course, you'll be using SAS Studio. SAS is a very powerful statistical software package. Looking at all the windows, menus, and features, though, can be rather daunting. So it's important for you to realize that this course will introduce you to the basics of SAS. You will learn what you need to know to get started asking and answering interesting questions about data.
In the beginning, it may feel like you're learning another language. Basically, you are. As you work through your project, you should begin to feel more comfortable implementing the various decisions you'll be making about the data. When you need help, seek it from your course moderator, professor, your peers, or from course discussions.
No.
Now you need to register for SAS On Demand for Academics. To register, follow the directions on the SAS registration page open in one of your windows. If you require additional registration instructions for the SAS On Demand for Academics SAS Studio, click on this link. And scroll down to the Students section. Click on the SAS Studio link under Quick Start Documents. After you've replied to the SAS email and finished the registration process, click the link below to enroll in this course. Here's a helpful hint. Bookmark the SAS login page so you can access it easily. From now on, you'll be working with SAS Studio in one browser window and this course in another. This can get really confusing if you're not familiar with using multiple windows in your web browser. There are many ways to do this. The easiest is to simply open two browser windows and place them side by side. You can easily create this layout with the following steps. Reduce the size of your browser window so that it fills half the screen. Click on the link below to take you to the SAS registration page. This link will open in a new tab in your browser. Grab the tab, like this, and then position it side by side with this window. Depending on your browser, you may have to resize and arrange the windows by dragging on the corners. When you're finished, it should look something like this. Now you're registered with SAS On Demand and enrolled in this course. It's time to start learning to write a program. Log into SAS Studio if you're not already logged on. Once you log in, you'll see the SAS dashboard. Click on SAS Studio. The following videos are full of important information. They introduce you to writing code in SAS. Please work at a comfortable pace and stop the video to work on your own program and incorporate what you're learning as you go along. Here's how to begin. This is your main screen. On the right-hand side of this screen is a new empty program window, which looks like this. In SAS, the program window works much like a word processor. There are a few basic steps that SAS and all other statistical software languages require when you begin writing a program. First, you will call in or point to the data set that you will be working with. You'll use the libname statement to do this. Libname is short for library name. You can copy the statement from the text below this video and paste it into the SAS Program window. And this is the first line of your program. It's the same for everyone, and you'll never need to change this line in your program throughout the rest of this course. The libname statement simply tells SAS where to find the data. It's important because it will allow you to successfully access your dataset. The name MyData within the statement is a label chosen as the name that the dataset will be given when it's stored within the SAS library. Next, the path name, enclosed in quotation marks, provides the location in the SAS cloud where the data is being stored. Finally, you'll include access equals read only so that the raw data cannot be modified. A very important feature of SAS syntax is that every SAS statement ends with a semicolon. Without a semicolon, sometimes called a command terminator, a SAS command is incomplete, and this will cause errors when you run your program. Notice that SAS uses color coding to help you write and debug your program. Remember, you don't want to see red in any of the code you write. You do, however, want to see blue, purple, and sometimes green. Blue font indicates a SAS keyword. Keywords are a primary part of SAS programming language. They're part of the established SAS lexicon. Most SAS statements begin with the keyword, just as all SAS statements end with a semicolon. Purple font indicates that SAS considers this section of your statement part of a string. A string in SAS consists of consecutive alphanumeric or other characters enclosed by single or double quotation marks. Green font indicates that these are your statements, the code writer statements. They're kind of like notes to yourself about part of your program. They're usually enclosed within asterisks and forward slashes, and they're not analyzed by SAS. If you write a line of code and absolutely none of it appears in one of these colors, you only have black font on a white background, then you want to take a closer look and see what needs to be corrected. SAS is generally not case sensitive, so whether you write your programs in lower or uppercase letters or a combination of both, SAS will be able to read it successfully. Following the libname statement, The SAS program requires a data step. The data step reads in your specific data set and prepares it for use. The word data indicates to SAS the beginning of a data step in which a temporary data set is created. Here, the data set is assigned by the word new followed by a semicolon. Next, the set statement is used to tell SAS which data file to set for analysis. My data is the label created in the libname statement above, and it's followed by a period. NESARC_PDS is the actual name of the NESARC data file located on the SAS cloud server. If you chose the Mars Crater dataset, NESARC_PDS would be replaced with Mars Crater_PDS. For the National Longitudinal Study of Adolescent Health, the name would be changed to AddHealth_PDS. If you chose the Gapminder dataset, the name will simply become Gapminder, and so on. To end the data step, there are different options. Here we'll end with a proc statement. A proc statement is a procedure statement which indicates to SAS you want to perform some manipulation of the data. This is a proc sort statement. It's asking SAS to sort the data according to one or more variables. A good habit to get into is to sort the data according to the variable that uniquely identifies each observation, that is, the unique identifier. In the NESARC dataset, the unique identifier is called ID num. So this line of code is telling SAS to sort the data in the NESARC dataset by ID num. Remember to always end a command with a semicolon. At this point in the program, you should write this line of SAS code using the name of the variable that uniquely identifies the observations in your dataset. These can typically be found in the codebook. By consulting the codebooks, you'll find the unique identifier for the Mars Crater data is ID. The unique identifier for the AddHealth dataset is AID. The unique identifier for Gapminder is country, and so on. Now that you've ended the data step with a sort statement, all procedures that follow will be written to request specific output or results. Now's the time to save the program you've started. To do this, click the Save As button above your main program window. This button is located just to the right of the Save button. The default name is Program, but you should feel free to rename the program as you like.
Remember, we stated exploratory data analysis begins by looking at one variable at a time. This is called univariate or descriptive analysis. In order to convert raw data into useful information, we need to summarize and examine the distribution of any variables of interest. The variables of interest are the variables of interest to you, the researcher, in answering your research questions, addressing your research problem, and telling the story you wish to tell with your research. By distribution of a variable, we mean what values the variable takes and how often the variable takes those values. Here's an example.
A random sample of 1,200 U.S. college students were asked the following questions as part of a larger survey. What's your perception of your own body? Do you feel that you're overweight? About right. Or underweight? This table shows part of the data, 5 of the 1,200 observations. Information that would be interesting to get from this data includes what percentage of the sample students fall into each category. Or, how are students divided across the 3 body type image categories? Are they equally divided? If not, do the percentages follow some kind of pattern? There's no way that we can answer these questions by looking at the raw data, which are in the form of a long list of 1,200 responses. That's just not very useful. However, all these questions will be easily answered once we summarize and look at the frequency distribution of the variable body image. That is, once we summarize how often each of the categories occurs. In order to summarize the distribution of a categorical variable, we first create a table of the different values or categories the variable takes. How many times each variable occurs, which is the count, and more importantly, how often each variable occurs, which is expressed by converting the counts to percentages. Now that we've summarized the distribution of the body image variable, let's go back and interpret the results in the context of the questions that we post. What percentage of the sample students fall into each category? How are students divided across the 3 body image categories, and are they equally divided? You can see that most of the samples, that is 71.3%, felt that their weight was about right, and that a comparatively small percentage felt underweight at 9.2%. The overweight category was 19.6%.
Go back to your SAS program now to learn how to use the frequency procedure, which is what you use to generate distributions for the variables of interest that pertain to your research question.
The frequency procedure is typed as proc-freq, and it's followed by a semicolon. Next, include the table statement, typed as tables, followed by a list of variables that you would like to examine.
For my research question, I'm interested in looking at the association between how much a person smokes, that is, quantity and frequency of smoking, and the presence or absence of nicotine dependence. Going back to the NESARC codebook, you may recall that I have a number of variables that measure smoking behavior and nicotine dependence. It's the actual name of the variable, rather than the longer descriptive name, that I'll include in my program in order to generate frequency distributions. I have the names of each of the variables circled here in red.
Here's an example of a NESARC program with the frequency procedure and table statement added. Then a run statement is added at the end of the program. The run statement is responsible for executing all the previously entered SAS statements in this program. When you add a proc-freq and table statement with your own variables of interest from the data set you've chosen to ask your research questions about, and then conclude with a run statement, you've written an entire SAS program. You will build on this program as you progress through your project. Before you run the program, it's always a good idea to save it. Click the Save button at the top of the program window. After you save the program, you can run it by clicking on the Run button at the top of your program menu. SAS Studio has 3 different tabs located at the top of the main program window. You write your code on the page marked by the Code tab. Just to the right of the Code tab is the Log tab, and to the right of that is the Results tab. Once your program is finished running, either the Results tab or the Log tab will open. It's a very good habit to get into to check your Log tab first after running a program, so you can check for any errors in your program. When you click on the Log tab, you'll see a section at the top of the page entitled Errors, Warnings, Notes. If any errors were detected in the program, the number of errors located in parentheses will be listed to the right of the red X errors icon. The same with any warnings or notes. If there are any warnings, the number will be listed in parentheses to the right of the yellow triangle warnings icon. And any notes SAS has about your program will be numbered, again in parentheses, to the right of the blue I circle notes icon. If you double-click on any of these icons that indicate the number of errors, warnings, or notes that exist in the program, then a list will appear beneath the double-clicked icon. If you do find any errors listed on the log page, go back to the code page, correct the errors, save the corrected code, and then run your program again. If no errors are listed on the log page, click back to the results page and you'll see the results of your program. In this case, it will be the distribution tables you generated. In this example, our program is run successfully, and the notes, listed in blue font, tell us a few things. It tells us the reference library, which was called My Data, was successfully assigned. Also, there were 43,093 observations read from the dataset NESARC.
That's good news, since I know that is the number of observations or individuals in the data set. If the number of observations seems incorrect, it's possible there may be a problem with the program that processed the data incorrectly, rather than actually generating an error message.
If your program ran successfully and there are no error messages in the log, then go ahead and click the Results tab to see the frequency tables that were generated for each of your variables. Because the actual variable names are cryptic, it's a good idea to give them labels that are more easily interpreted at a glance. We'll use our NESARC program as an example and show you how to generate variable labels in your program. SAS programs are made up of two distinct steps, data steps and proc steps. You write data steps, which enable you to manage and manipulate your data. You're writing code telling SAS exactly what to do with your data. Proc, or procedure steps, enable you to analyze and present your data. Proc steps are pre-written procedures, so the code in the proc step is not giving SAS instructions to execute like the code you write in a data step does. The proc codes you write basically control how the proc step runs. With this in mind, you're going to enter your label statement here. Labels require the use of the term label. Then you enter your variable names. Each variable name is followed by an equal sign, and then the new descriptive variable name within quotation marks. Once you've completed the list of your new variable labels, this label statement, like all SAS statements, ends with a semicolon. Then save your program and rerun it by clicking the Run button.
I check the log, which shows no errors, and then I view the results. As you can see, now my frequency distributions include both the variable name and the variable labels. If I look at the first table, which shows the distribution of responses for the variable tobacco dependence in the past 12 months, I know from consulting my codebook that 1 means yes and 0 means no. Following this list of response options, the table also shows the frequency of each, the percent of individuals with and without nicotine dependence, the cumulative frequency, and the cumulative percent. By consulting your codebook, you can interpret and describe each of these frequency tables in the same way.
Once you've examined frequency tables for your variables, the next decision you need to make is whether you want to subset the data and ask a question based on specific observations, or whether you want to ask the question of the entire sample. In other words, are there particular rows in the data set, that is, individual observations, that you want to keep and others that you want to exclude? For example, we're most interested in the association between smoking and nicotine dependence in young adults who may still be establishing their smoking patterns. Therefore, we decide to examine only those adults who are 25 or younger and exclude all adults older than the age of 25. We also decide that we want to focus on recent smokers rather than individuals who've smoked more than a year ago. So the original research question for our example is further clarified to include the association between smoking and nicotine dependence, but only among young adults who have smoked in the past 12 months. The research question is not changed. Rather, the question will be asked based only on a subset of the observations that are available in a specific data set that will help answer the research question. To implement these decisions, we'll go back to our program and add 2 additional statements just before the end of our data step. These additional statements are logic statements. Specifically, you need to add logic statements that tell the program to include only those observations that will help you answer your research question. Logic statements require 1 or more operations. Here's a table of common operations used in SAS. These include equal to, not equal to, greater than, less than, greater than or equal to, and less than or equal to. The following logic statements will need to be added to this program in order to call in the specified subset of the observations now to be used as the basis of the research question. If check 321 equal to 1 semicolon, which is the variable for cigarette smoking status in the past 12 months, and if age LE 25 semicolon, indicating selection of only those individuals less than or equal to 25 years old. These logic statements go at the end of the data step before the proc sort statement. The variable age should also be added to the table statement so that distribution can be examined. When this program is saved and rerun, you can see frequency distributions for each of the variables, but only for the 1,706 individuals aged 25 and younger who reported smoking in the past 12 months.
I can be confident that I am now working with this sample because, as you can see, all of the 1,706 observation has a 1, meaning yes for having smoked in the past 12 months. And if I scroll down to the distribution of age, I can see that only 18 to 25-year-olds are included in the sample. If for your own research question you are completely unsure at this point whether or not you want to limit your question to a subset of observations, no worries. In that case, there would be no need for you to add any additional logic statements to your program. This is always a decision and an example that you can revisit in the future.
Here's a way to add notes to your program to help you remember what specific lines of code do. As you keep adding to your code, it might become difficult to remember why you wrote what you wrote. You can comment out your notes so that SAS doesn't read the notes as actual program statements. The method for doing this is to include your notes in between a /* and a */. Here's a note added to our example code. It's a note to remind ourselves that the data is being subset to include only past 12-month smokers age 18 to 25. The note is written in green within the program. You can be confident that it will not be read as SAS syntax. You should definitely use this commenting out technique early and often as you build your own program. These notes can be very important because they will help you keep track of decisions you've made and actions you've taken in writing your code. At this point, and whenever you've added something to your code, you should save it.